Okay. So we are discussing spectral projections for self-adjoint operators. So there is a, I mean, we prove certain facts which we may not remember. I will recall it whenever I use it. So we want to prove, first we want to prove a criterion by Holmos to determine when a vector belongs to a spectral projection corresponding to an interval. So we want to deal with intervals. So this is the following proposition. Incidentally, we are using strong convergence. I mean, we are basically using, we are working with strong convergence when we use projection, because normally projections will never converge I mean, unless it's a peculiar sequence, will not converge in norm. It will converge, for example, if you can have, I mean, for example, if you have a Hilbert space H and it is just a span closure of some orthonormal basis, okay, then you can, Hn is a finite dimensional subspace even up to En. Can Pn be the projection from H to Hn? This Pn, we say Pn increases to P. I mean, Hn increases to subspaces, Hn increases to H. Union of Hn, closure is H. So Pn increases, this is strong convergence. It is true that P and Xi will converge to P Xi. Okay. But if you take but it will not converge in norm because Pn will converge to identity. I mean, P means its identity here. Okay. If you take 1 minus Pn, that is also a projection. So its norm is 1. So this cannot go to 0. Most of the time, if you take projections, P1 minus Pn, I mean, it will be a projection, it can be something, it will not converge in norm. Okay, so we have to use strong convergence. So it's important that we are using, that's why we are using strong convergence. So whenever we say converging, projection converge, it's in strong, I mean, I will write, even if I forget to write, it's in strong convergence. So this is the following proposition. So let T be self-adjoint operators. The following conditions are required. One, so the Xi is a vector, the H, and Xi belongs to the spectral subspace. I mean, this is, we write the T in the, here, no? T minus 1, 1. It corresponds to the perspectral subspace corresponding to the interval minus 1, 1. Xi is here. This is equivalent to, okay, just two, I don't want to, there is another statement which is not needed, which will be part of the proof, but it's not needed. So this set, T power n Xi, m by n, is bounded. So proof. So 1 implies 2. We want to, so when Xi is in this, we want to prove that this is bounded. Okay, that will, so notice that, so, I mean, this projection, this, of course, this commutes with T, of course, and you can define T0 to be, this commutes with this. So the subspace corresponding to the, I mean, some projection, I hope you know that. If you have a P which commutes with some operator T, then that means that, I mean, you might have seen it in linear algebra, the same thing is true in general Hilbert space also. If you have a projection P commutes with T, that means this, so this projection has a subspace, which is called it as H naught. And there is a H naught per, which is equal to H. Okay, that's how it will look. I mean, P is a projection onto some H naught. There is a subspace corresponding to this P. Then there is an orthogonal complement so that this holds. Okay. Now this T can be, so this is like, this H is decomposed into two subspaces. So any operator on H can be written as a matrix like this, where this is an operator from H naught to H naught. This is an operator from H naught perp to H naught. This is an operator from which takes H naught into H naught perp, and this is from H naught perp into this. So if you have any vector xi1, xi2, it is exactly like the matrix operation. It's like that. If T commutes with that, you just then P can be written as 1, 0, right? P is just 1, 0. This P is nothing but 1 with respect to this decomposition. This projection is 1, 0, 0, 0. It's like that. You just write matrix product. It's exactly the product is exactly the matrix product. You get convinced about it. Then you just write the matrix product and use the fact that PT equal to TP. That will imply that T2 equal to 0 equal to T3. You'll get this. This is an exercise. You do this and you will get T2 equal to T3. They are 0. So if we have if an operator, any operator, I mean here it's self-adjoint, we don't need that. If an operator commutes with these, then that just means that it will look like this. Maybe it will look like this. So this just means that it leaves both H naught and its orthogonal complement invariant. Okay. When it is self-adjoint, I mean if something leaves H naught invariant, some T leaves H naught invariant, T star will leave H naught perp invariant. You can check that. It's basically linear algebra. Okay, you can check that. So if it is self-adjoint, if it leaves H naught invariant, it will automatically leave H naught perp invariant because T equal to T star. Okay. If it is self-adjoint. Okay. So if we have, so usually when you want to restrict an operator P to the subspace corresponding to the projection, you usually write it like this. This is the restriction. You hit it in both the ways, so that it acts only on this. I mean, if you have a operator T1, T2, T3, T4, then this PTP is nothing but just T1 here, 0, 0, 0. Okay. So, but if it commutes, you don't need it. You can put, I mean, you can multiply P in one of them, and that will give the restriction. Okay. Now we take, so this is just about some projection since we haven't done all these things. So now you take this. This is equal to minus 1, 1 T of P. Okay, this is an operator. T naught is a new operator, which is just the restriction. Then, as I mean, the earlier one, so minus 1 is less than or equal to this. This is 2, no? Okay, less than or equal to 1. This is, I mean, just functions. For functions, this is true. So this implies T naught. T naught is the greater than or equal to 1. This is identity. This one is identity. This is less than or equal to 1h. This is operator. I mean, operator less than or equal to. This means this minus this is positive. This minus this is positive. I mean, the measure. This is the inequality for functions. Then the same inequality holds for operators. Okay, because any homomorphism of physical algebra respects the less than or equal to positivity. Respects positivity. Okay. Okay. So, I mean, so from this you can see, so if we already know that if an operator S is positive, then we know. I mean, S is positive, then sigma S is contained in 0 infinity. Okay. So if T minus E0 minus 1 is positive, that means the spectrum of T0 minus 1 will be contained in 0 infinity. That just means that spectrum of T0 is contained in minus 1 infinity, end of thing. I mean, because it's a spectral mapping theorem, it's just a, I mean, polynomial, you can, I mean, even for continuous functions, we approve, okay? From Amrit, I just want to complete some, I mean, I want to, this is just contained in this, okay? Okay? This is clear, okay? I'm just saying from this, and spectral, combined with spectral mapping theorem, implies that, say, the spectrum of T naught is contained in minus 1, 1. And it's T minus 1 is greater than 0 and 1 minus T is greater than 0. That from that it will follow. Yeah, from that this will follow. Okay. In particular, norm of T naught is less than or equal to 1. Okay. Because it's self-adjoint, spectral radius is equal to the norm. Okay, so if you want, R of T is less than or equal, R of T equal to 1. So this is equal to, I mean, sorry, less than or equal to. Less than or equal to. Spectral radius is less than or equal to 1. So the norm of T naught is less than or equal to 1. So this implies T is I And in fact, this is also true that, I mean, so this implies T xi is less than or equal to norm xi. If, I mean, T xi is equal to T naught xi, of course, if xi is in, I mean, if xi is in that. What is the MT minus 1? Okay. If xi is in this subspace, then of course you can insert that projection there, and this is equal to this, and that is less than or equal to norm xi. In fact, you can take T and xi, okay? You can insert that projection, that I minus 1 T, that projection, and you can insert it any number of times. Of course, it's a projection. So you can keep it with this, and all of this Tn power n also will have norm less than 1. So it's clear, right? So it's bounded. Okay. So xi belongs to that subspace, then this sequence is bounded in norm. Okay. I mean, they are all less than or equal to 1. It's in n, bounded in n, so they are less than or equal to norm xi for all n, so it's bounded. Okay. Conversely, so if this is okay, we'll go to finish that part. Okay. And we haven't done anything. We just use this fact, and then it shows that the norm of this. I mean, in fact, T0 is less than this. Sigma of T0 is contained in this. T power T0 power n is also contained in this, and from that follows. Okay. Now, suppose this T and xi is just bounded. Then we want to prove that xi is in the spectral subspace. Then we want to xi is in array. That is, we want to prove 1 upon 1 of T of xi equal to xi. That's what we want to prove. That is, we want to prove I mean, this is identity. Identity is IR. Okay. I mean, identity is the whole real line. I mean, spectral projection corresponding to whole real line. Okay. That may, I mean, see, incidentally, we are using spectral projections for any interval outside the spectrum. It is 0. Okay. I mean, spectral projections are sets contained in the spectrum. For bigger set, we are taking the intersection with the spectrum and using it. Okay. But if you have any E in R, for us, if you have an E contained in sigma of T, then we define this, right? Using measurable functional calculus. If you have a E in R, then you can have E intersection sigma of T. Okay? That is a spectral projection. Okay? Same as E. Okay? Where is P? To prove. to prove. This is all to prove. ETP enough to, when I say ETP, it's enough to prove. Yeah, this is to prove. Sorry, T also has a meaning, P also has a meaning here. So we use T, we use P to prove. Okay, this times xi is 0. This is what you have to prove. Okay? So this is 1 minus this is, I mean, they are, you just remove the set. Okay? This is 1R minus 1, this R minus this. Okay? So this is 0. And enough to prove 1 or minus you take you remove a bigger interval, minus 1, 1 by n, 1 plus 1 by n, t acting on say equal 0 for all n. Okay. Since, I mean, these sets decreases, these sets are, you are taking, you remove a bigger interval. So these sets decreases, no, increases, right? These sets decreases to minus 1, 1. Those set increases to minus 1, 1. I mean, that's it, r minus minus 1. Okay. Since as projection, this T, these are all projection, this increasing in the strong sense. Okay. This increases to 1. Okay. This is in the strong convergence. Okay. By increasing, we mean strong convergence. This follows from the property of the measurable functional calculus. If some function f1 converges to f in mu, then f1 of t converges to f of t strongly, provided they are non-modulate. In particular, if the sets are increasing, then they will converge in mu. I mean, they will converge almost everywhere, in fact. So from that. Okay. So we only need to prove this. Okay. So for each n, so we call that projection as Pn. We call that Pn. So suppose we want to prove that for all n. Suppose P and Z equal to 0, P and Z not equal to 0 for some n naught. Suppose. Okay. Then we want to get a contradiction. We want to prove that that's not bounded. Okay, our assumption is that I have some problem in the tongue. So our assumption is that this is bounded. Okay. So we want to contradict that if this is not equal to 0. Okay. You call this as some yn naught. Xi n naught. That's better. Xi n, so Xi n naught. Okay. We have proved something. If you remember, we proved the following. If Xi is in spectral projection of R minus this interval, P naught. I mean, sorry, this is open interval, okay? Please think this is open interval. I mean, we are having that as closed interval, no? We can work with open interval. This is open interval. So this is open interval. We want to prove this is equal to this. So if you read, if you R, I mean, R minus minus 1 is, oh, so no, this is closed interval. Sorry, this is closed interval. It's okay. The convergence is open interval. I mean, this open interval will decrease to this closed interval, right? Yeah. This is open interval. Sorry, that is closed interval. It's okay. So if you have this t minus epsilon, t0 plus epsilon, okay, I mean, it's in the range of this. Then we proved that then norm t xi, yeah, norm t xi is greater than epsilon times xi. Right? This is what we proved. T minus t naught. Yeah. T minus t naught. Here t naught is 0. Yeah, right. In this case, T naught is 0 and epsilon is 1 plus 1 by n. Okay. So we have T of xi n naught is greater than or equal to 1 plus 1 by n times norm of xi n. Okay. 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 Now I want to compute t power n. This is n not is fixed, but that's okay. T power n of xi. Okay. This is greater than or equal to. If you apply a projection, norm will decrease, right? Huh? This is from t naught is 0, epsilon is 1 plus 1 by n here by applying that. I mean, epsilon is small, but here it is big. Yeah. Usually epsilon is small, but yeah, here it is a big epsilon, 1 plus 1 by n. Is greater than 1 of that r minus. There is a 1 plus. Sorry, this is 1 by n naught, right? 1 by n naught, not n. Okay. 1 plus 1 by minus 1 plus 1. Okay. Of t times t power n. Okay. Now, this commutes with Tn. You can have any power of this if you want. You can take it here. Okay. So this becomes In naught. Okay. You first, but then you have t power n minus 1. But then T leaves that subspace invariant, right? T leaves all the spectral projection invariant, right? What I'm saying is t power n minus 1, that whatever this projection, we call it Pn, Pn naught, okay, Pn naught acting on xi, okay. This is also in that range of Pn naught. Okay? Pn naught is that subspace. Okay? Because this commutes with all t. I mean, this commutes with t. Okay. I mean, it commutes with t power n, everything. So you can take it, and what this says is from, I mean, it get convinced this is greater than or equal to 1 plus 1 by n naught power m times norm of xi n naught. You take this here, it becomes xi n naught. But you can have any power of this because it's a projection. Okay. And you can have so first t acts on that. That takes it into the same subspace because t leaves all these subspaces invariant. So you have another element of this. Okay, apply t on that. This is true for any xi in the subspace, right? Okay. I mean, for all xi here, this inequality is true. Okay. So you apply. Okay, it's clear. We get convinced. I mean, you have a xi, you act this projection. You can get this projection past this, and you can apply this. Once you apply a t on that, I mean, if you have a big T here, you have a first T here, and Tn minus 1, that thing, that is again contained in that, that subspace. So that inequality is there, so you continuously apply it. And finally, you will get 1 plus 1 by n naught times xi n naught. Okay? Applying T1, I mean, using this fact again and again. This is, I mean, this is for the first one I have used, but if you use it for n times, you will get this. Okay? But this goes to infinity as m goes to infinity, which is a contradiction. Okay? Video has gone. I don't know. Okay. So, okay, so this is the criterion. So from this we get the following corollary. So one, so this is the corollary. Yeah. Xi is in the spectral projection corresponding to this subspace M T of this T naught minus epsilon, T naught plus epsilon. Any such thing. This is equivalent to T minus T naught divided by epsilon and Xi over N is bounded. Is clear? Okay. I mean, this will imply that Xi is in the spectral projection of corresponding to -1 of this. That is exactly equal to, we have gone through that. That is exactly equal to the spectral projection of T corresponding to this interval. We had an exercise, the one, F inverse something. If you use that, you will get it. Okay, we stated. Right? You take the function, which is T minus T naught by epsilon. You take that function and apply the criterion, so you'll get this. Okay. So this is clear. Okay? No need to prove. Another corollary is, let S in B of H. This is also self-adjoint. Okay. And T is, of course, ST, both are, S is need not be self-adjoint. I think S is not self-adjoint. S is just B of H. Let's see. Okay. T is in B of H. Self-adjoint. Okay. S need not be self-adjoint, I think. Let's see. Okay. Then, and no, it's better it's self-adjoint. Okay. Both are self-adjoint. Because when I say it leaves invariant, I want to say it leaves a complement also invariant. Whenever I say invariant, it leaves both the subspace and complement invariant. So ST or G of H, self-adjoint. Okay. Okay. And okay. So I contained in R, any interval. Of course, we work with any interval means open, close, half close, whatever. Okay. So the point is, if you want to work with spectral projection, it's enough to consider bounded intervals. Okay, unbounded interval, you are going to take intersection with the spectrum, which is a compact set. So it's enough to work with bounded interval. Okay, so unbounded interval means it's same as bounded, taking the spectral projection with bounded. Okay. So STR operators and I contained in be any interval, then S leaves any interval, S leaves M T I invariant. That's all. Sorry, I forgot to say, it commutes with that. Okay. And ST equal to TS. Otherwise, there's no point. Then, and ST lives in for I contained in R interval. Okay. S leaves this subspace invariant. Okay. Now we are assuming self-adjoint. So we only have to prove that if you have a Xi in this interval, then Si is also in this, in this subspace, then Si is also in this subspace. That's what you have to prove. Okay. proof. So let first let I equal to T naught minus epsilon, T naught plus epsilon. Okay. I mean, any closed interval will look like this. First, we will prove for a closed interval, and it is enough to prove for bounded intervals, right? Maybe I'll write that. Enough to prove for proof. Bounded intervals. Okay. And first, I mean, assume let I equal to, I mean, we will prove for another open interval from this by taking union and the intersection, union and intersection. Let I equal to this, some T naught plus minus epsilon, T naught plus epsilon. Okay. And so we want to show that S leaves this subspace invariant, this subspace, MTI. Okay. That Xi is in MTI. We want to show that it leaves this subspace invariant. You just write the criterion and I mean use the property of the bounded operator, it will follow immediately. Okay. Now Xi is in MIT, MTI. Okay. This just means this is equivalent to saying that T minus T naught by epsilon of Xi. This implies Xi power n is bounded by the criterion. Okay. But then if you have a bounded operator, it takes bounded sets to bounded sets, right? The bounded operator is something which takes bounded sets to bounded set. So S of T minus T naught epsilon power n Xi is also bounded. Okay. But S commutes with all these things. Okay. But S commutes with this. So this implies that's all. This is for this specific compact interval, for this closed interval. So if T equal to, I mean, I equal to AB, take IN equal to AN, BN, closed interval, such that AN, BN as sets increases to AB. Okay. Then again, as projections will increases to MTI strongly. I mean, by this it means strong convergence. Okay. If you take an element here, and if you apply Pn Xi, Pn is a corresponding projection corresponding to this means Pn Xi will converges to P Xi, okay, for all Xi. Okay. So, but that's what it means when I write strongly. When I say the projection increases or the subspace increases. Okay. So now it leaves. So that is MTI equal to MTIN union N in N, and you take the closure, right? Okay. Now, if S leaves all the subspaces invariant, it will leave the union invariant, and it will leave the closure also invariant because it's continuous, right? Okay. So this implies S of MTI contained in MTI. Because for all IN this is true, so for I also this is true. Because it's just the union of all those things. So by this, when this increases to this means, by this we mean this. We mean precisely this. Union of all the subspaces, take the closure, that is this. And it leaves all the subspaces invariant, so it will leave that invariant. That's all about this. Okay. Now we want to make a definition. We want to generalize the notion of spectrum for n number of operators, n number of commuting operators. So suppose T1, T2 up to Tk or in B of H, they are all self-adjoint. Later we use normal operator. They are all self-adjoint and commuting, mutually commute. That is Ti, Tj equal to Tj, Ti for all I. They are mutually commuting. Then define sigma of T1 to Tk. Okay. They are self-adjoint operators, so their spectrum is contained in Rk, and this will also contained in Rk. I mean, the spectrum is contained in real line. This will be contained in Rk. This is equal to all those lambda 1 up to lambda k in Rk such that Ti minus lambda I such that there exists xn with norm xn equal to 1 and Ti minus lambda I xn goes to 0. This just says that these lambda i's have an joint approximate eigenvalue. I mean, sorry, joint approximate eigenvectors. I mean, when we say eigenvector, it is, I mean, it's a sequence. Okay, but what it actually means is, I mean, eigenvector says the following. If you have a single eigenvector, this just says that sigma lambda xn, this goes to 0, right? But this actually means that xn, after some time, this will be less than epsilon, right? So this basically says that given epsilon, we get an x. I mean, you can use 1 by n or epsilon, and I mean, it does not matter whether it's continuous or something. Given epsilon greater than 0, you get an x epsilon such that this is less than epsilon. That's what it means. With norm x epsilon equal to 1. That's just 2. Okay. So that's what this says. So this, I mean, if you have an epsilon eigenvector, and if you call this x epsilon as epsilon eigenvector, or this xn as 1 by n eigenvector up to approximation, so then this is that there's a joint eigenvector for all of them. And for normal operators, something is in the spectrum if and only if it's an approximate if it does not, if it admits approximate eigenvectors and sequence of approximate eigenvectors. So this is the definition. So it's important that this xn is joint. It works for all. I mean, this is for. I mean, this is true and for all I less than or equal to k greater than or equal. I mean, Ta minus lambda I xn goes to 0 for all I. Okay. So now the proposition. First one sigma T1 up to Tk is compact. I mean, it's non-empty, will follow from this. And pi I of sigma T1 up to Tk equal to sigma of Ti for all I, where phi a is this projection which takes some lambda 1 up to lambda n to lambda I. Ith projection onto the ith coordinate, not the projection operator, it is a function. Right? Function which is projection onto the ith coordinate. This is also an operator, of course, projection operator, ith subspace on our. So this will imply, in particular, 2 implies sigma of this Pk is non-empty. Because if you project it onto the ith coordinate, you get a non-empty set for each I. So this is supposed to be non-empty, of course. So we have to prove it's compact and we have to prove this. Okay, proof 1. You want to prove it's compact. So if something, I mean, some element is, so if lambda 1 up to lambda n is in the sigma of that, then lambda I is, of course, in sigma of Ti. Other way it need not be true. Because, I mean, if it is a joint approximate eigenvector, it's a eigenvector for each Ti. Okay. So this implies sigma of T1 up to Tk is contained in sigma of T1 cross sigma of T2 cross sigma of Tk. Okay. So this is compact, this is bounded. So this implies this is bounded. It's contained in a bounded set, so it's bounded. So we only have to prove it's closed. So to prove sigma of T1 up to Tk closed, so you take a sequence and you have to show the limit. If it converges, the limit is here. So let us take lambda 1 n to lambda k n converges. This is in that sigma. Okay. Converges to some lambda 1 up to lambda k. You have to show that this is the limit is there, such that is, I mean, of course, it's finite dimensional. So convergence in Rk is same as point-based convergence. That is lambda I n minus lambda I goes to 0. Okay, that's what it means. Okay, for each side. So given epsilon greater than 0, since it's a finitely many of them, finitely many sequence, so we can get a single n. There exists a n naught such that lambda I minus lambda I n naught minus lambda I is less than epsilon, maybe epsilon by 2. So this is because there are finitely many of them. Okay. Okay. Now for this n naught, I choose an eigenvector. Okay. Now choose x n naught, not x n naught. I mean, now choose. I mean, now for this, so as I said, if it is an approximate eigenvector, which is a sequence, means that for each epsilon, there exists a epsilon approximate eigenvector, right? I mean, choose. I mean, for this epsilon, choose x epsilon. Okay. I mean, the n naught is inside that, such that lambda, such that Ti minus lambda I n naught x epsilon is less than epsilon by 2. This is possible, no? Because lambda 1 up to lambda, I mean, E for all I. Okay. Because lambda E1, lambda 1 n naught, lambda, I mean, no, because this collection, when you fix a n naught, lambda 1 up to lambda n naught, lambda k n naught, that is in that giant spectrum. So because of that, this minus this, there exists an x epsilon satisfying this. The same x epsilon satisfies that. That's what we want to prove. That's clear, right? Now Tn minus Ti minus lambda I x epsilon is less than or equal to Ti minus lambda I n naught x epsilon plus lambda I n naught minus lambda I x epsilon. But x epsilon is norm 1. This is just a scalar. This has norm 1. So this is less than or equal to epsilon by 2 plus epsilon by 2. Okay. We take an approximate eigenvector corresponding to this n naught and then work with it. So these things imply that lambda 1 up to lambda k is in that giant spectrum, sigma of T1 up to Tk. So it's very easy. You take a limit and then consider the right? It's very easy. So we have proved it's bounded and closed, so it's compact. So one is proved. Okay. Now we want to prove 2. So we prove by induction. Of course, true for k equal to 1. When k is 1, it is just one vector, and it is same as approximate. I mean, since t is self-adjoint, which is normal, we have only, there's nothing. Okay. Sigma of k, any t is sigma of single t is sigma of t. Okay. By definition, because it's normal. Okay. So suppose the whole statement, okay, 2 is true for k, and we want to prove for k plus 1, assuming it's true for k. I mean, the statement, you take any collection of T1 up to Tk, and it's if you project it on the nth coordinate, you get sigma of Ti. Okay. Then you want to prove it for, incidentally, remember that there is no ordering involved in this, right? Sigma of T1 up to Tn is same if you, I mean, this is just the definition does not involve this ordering. There is just the collection which matters. There is nothing to do with the ordering. So let Tn plus 1 in B of H be self-adjoint. I mean, so let's see. So suppose if it's true for k, let T1 up to Tk plus 1 be self-adjoint. Okay. And this holds true for sigma, I mean, up any k elements, then we want to prove it for a k plus 1th element. So we only need to prove so it doesn't matter which one you project. It's enough to prove for the k plus 1th element because the ordering doesn't matter, right? Enough to prove pi k plus 1 of sigma T1 up to Tk plus 1, okay, plus 1 equal to sigma of Tk plus 1, right? This is what you have to prove. There is nothing about Tk plus 1. You can take, I mean, when anything is same proof, same thing is true. Okay? This is what you have to prove. Assuming the statement of statement 2 is true for k, okay, you have to prove this. That is given lambda in sigma of Tk plus 1, need to get lambda 1 up to lambda k in sigma of T1 up to Tk, such that lambda 1 up to lambda k and lambda k plus 1 is in sigma of T1 up to Tk plus 1. Okay. Right? That's what it means when the projection is there, right? So sigma need not be the direct product of all the spectrum. It is just contained in the direct product of the spectrum. And when you project it on any coordinate, you get the spectrum. See? That means for any given any lambda here, there exists some tuple such that when you attach that, that is in the this giant spectrum. That's what the statement means, right? Okay. Sorry, this is lambda. I have taken lambda, no? Maybe call it lambda plus 1. Lambda k plus 1. I call it k plus 1. It's better. Okay. We need to get a lambda 1 up to lambda k. Okay. See, there is nothing about this tk has to be non-zero or something. Zero operator will have 0 as an eigenvalue and spectrum is 0. I mean, there is no assumption about it. They are just commuting, that's all. So, what do you have to do? We have to produce an approximate eigenvector, a joint approximate eigenvector for lambda 1 up to lambda k. Okay. So now we have that lambda k plus 1, I mean, from tk plus 1. So we have proved that, I mean, this one of this set. So lambda k plus 1 minus by n, lambda k plus 1 plus 1 by n. Okay, this projection is not equal to 0. We proved that, right? For all n. I mean, we proved for epsilon. Okay. It is indeed the intersection is that for the singleton one. Okay. For each epsilon, for each n, this is not equal to 0. Right? So we proved this. Okay. Maybe you call this as Pn. Pn. Okay. Okay. And we know that each of T1 up to Tk commutes with Tk plus 1. So it commutes with all the spectral projection. That's what we have seen the earlier using the Halmos criterion. That's what we proved. If it commutes with those operators, then it commutes with all spectral projection. So by earlier position, by corollary, Ti commutes. I mean, Ti commutes means Ti leaves this Pn invariant. Ti commutes with it, okay. Commutes with it, leaves invariant, or same thing for projection. Okay. Ti leaves Pn invariant. Okay. Now, sigma of Pn, P1, Pn into up to this sigma. Pn P1 up to Pn of Tk. This is contained in, let's verify it, T1 up to Tk, right? That is because if you have a, I mean, if you have, remember that if you have a, these are I mean, these are all operators which is defined on Pn, and it is 0 everywhere else, right? You have something here and 0, 0 here. Okay. Then the approximate eigenvector has to come from this subspace. If it comes from somewhere, then that is going to remain. And if you multiply by scalar, it will not go to 0, right? So if you have an approximate eigenvector for this, that has to come from that subspace of Pn. Okay. So if that works for Pn, then Tn acting on that, this is true, no? Then, I mean, if you have a xi in range of Pn, okay, range of Pn, then Ti minus lambda I xi is exactly equal to Pn Ti minus lambda I. I mean, P and xi is all same thing, right? I mean, so sorry, P, this same thing as this. Okay? I mean, you can have a Pn here, but it will come like this. So it's Pn Ti minus lambda. Okay? It's the same thing. So if something is a joint again, I mean, something is some lambda 1 up to lambda n, lambda k is here, then that will be here. Okay. Anyway, I said the proof, but you convince yourself. Okay. So this is contained here. Okay. The other way may not be true because when you apply a projection, that may become 0. Right? I mean, if something lambda 1 up to lambda n is here, you have a vector, then you get it to a subspace. You can take the you can apply projection onto that vector, but that may become 0. You need to have norm 1, right? Okay, so that may not happen. So it's only this inclusion is true. Okay. So now this is true, and this is contained in this for all I mean for all n. Okay. And so, and we have assumed the 2 for I mean for k coordinates. For k set of operators, we are assuming this is the 2 is true. 2 means if you project it on the nth one, you get the spectrum of that. In particular, this is non-empty. Okay, by 2. We are assuming 2, so these are all non-empty. 2 says that if you project it onto the ith coordinate, you get the spectrum. So it is in particular they are non-empty. So all for any operator, this is non-empty. Okay, so these are all compact sets, and they are non-empty. Okay, this you call it maybe Kn or whatever. Okay, no, maybe not. Okay, call it Kn. Kns are compact, non-empty, decreasing, okay. So intersection of Kn is non-empty, right? Okay. And this is not counter intersection theorem. That is for closed set with diameter decreasing. This is it's clear, no? It's a follows. If you take a sequence in one of them, some xn in kn, that should have a subsequence that should converge, and that should be in the. That's one way. Or you can use the finite intersection property. If you right, I mean they are all contained in big compact set something. So it will be finitely many of them. They are all closed set, and finitely many of them has non-empty intersection, which is the smaller one. So the whole intersection should be non-empty. You can use anything. It's clear it's non-empty. So now choose lambda 1 up to lambda k in this inclusion. Sigma is non-empty. This inclusion. This is just you take Pn Ti minus lambda I. If you take a lambda 1 up to lambda n is in this, lambda 1 up to lambda k is here. You have to prove lambda 1 up to lambda k is here. So lambda 1 up to lambda k is here means Pn this minus lambda I xi this. This is I mean given epsilon, this is given, I mean this is less than epsilon. Okay, direct is as I epsilon. Okay, this is less than epsilon, but this is exactly equal to Ti minus lambda I xi, right? What is the difference? Same thing, no? Ti, I mean, if you have a P here, you can bring the P here because xi is in the spectral subspace. See, if it satisfies for P and Ti, then the xi has to come from the subspace. So you can insert a P here. You can. Say it again. If PNS, P is a projection, yeah, non-empty. I mean, non-trivial. Non-trivial kernel, yes. Yeah. And because PN and TI commute. PN and TI commutes, yes. So P and TI will also non-trivial kernel. So 0, 0, 0. The triple 0, 0, 0. That's when I get the form as possible. Okay, yeah. But if you choose P1, P2, Pk, then 0 cannot be an approximate eigenvalue for that. So I'm not sure if this is given the concept. You are saying if lambda is 0, it will not work. Yeah. Yeah, if lambda is 0, then there is a problem, right? If, confused. If see, this is I'm just wondering what's wrong with this. Ti minus lambda is equal to this, right? For when xi, so if xi may not come from that, that's what you are saying. Yeah, if lambda is 0, then xi may not come from that. Xi can come from outside. Only then it will happen. If, I mean, what I'm saying is, if we have a xn, if there is suppose Ti, I mean, for a general T minus lambda xn, okay? So it goes to 0, okay? And norm xn equal to 1. So if lambda is not equal to 0, okay, then xn has to come from that subspace, right? I mean, if you have Pn. Because if xn has some component outside that subspace, that will okay. Yeah. Lambda is not equal to 0, this will not happen. So only when lambda equal to 0, we have to worry about it. Okay. When lambda equals 0, as you say, I mean, lambda equals 0, you can have a invertible operator T, where the eigenvalue, I mean, where 0 will not be in the spectrum. But if you project it onto the subspace, 0 will be in the spectrum, right? So this is not true actually. So you have to take care of 0. And 0 in all coordinates. Yeah, good. I think there's a problem.